All right, we're going to get going. This is the last session of the day before we get to go down and see some of these ILI devices and smart pigs from some of the folks that will be talking. Basically, this was a look back at as technology advances over the last 20 years improved things. And what you're going to hear is a bunch of the vendors who have brought their smart pigs will be talking about that. But Max Kieba from PHMSA, who's the head in the engineering and research division, is going to give us kind of a broader perspective of what technology has changed over the last 20 years and how it's made things safer or not, I guess. So Max, take it away. Up and down buttons.
Yep, thanks, Carl. And yeah, I'm with our engineering research group, so one of the other fun things I get to do is all these new technologies that come out, and I can tell you every vendor thinks they're a game changer, but sometimes it takes a little while to take them and consider them. So as Carl said, I'm going to try to give you a slightly broader view, but I'll also focus on ILI, which is of primary interest here. I'll try to give you some examples of high-level improvements that have been made through the years, a couple of gaps and areas of improvement, at least that we see, whether it's through data or anecdotally, and give some ideas that things that can complicate advancement, and sometimes that is regulatory, where quite frankly, sometimes our regulations take a little while to get updated and lag a little bit. So just some examples of improvements we've seen or have influenced. Since this group is interested in ILI through the years, we've seen better detection of dents, cracks, metal loss. So the old days of it used to just look for metal loss of corrosion. You've probably seen some earlier presentations already today looking at cracks and other more detailed defects that can be very challenging to detect. We've also had a part of that with a lot of our R&D. Guided wave, for those that aren't aware of it, it's another assessment method that for harder to inspect areas, essentially you shoot electromagnetic waves down a pipe, and particularly these are areas where particularly if a pipe's in a casing underneath a roadway and for whatever reason it's difficult to detect. Guided wave up to now has been through what's called the other technology notification process we have. That's a means for operators to look at other assessment technologies. It is now finally in the 192 through the gas rule, or I should say it will be when the gas rule is effective in July. And to give you a sense of how long it took to get to this point, the first checklist probably came out about 12 years ago in 2007. So it's taken 12 years through learning of this technology, a number of processes. I mentioned we have this no objection process for other technology notification up to now. And through the years, both ILI and guided wave and a few others, we've better understand the process on how to use them and the technologies themselves. Just to give you a sense of our R&D, we do put a lot of R&D resources into, and this is just the technology-focused R&D, and we go to all kinds of areas of threat prevention, leak detection. I was going to mention leak detection as one of the areas we see improvements on, but I thought that was kind of ironic, given we just had a pretty significant spill recently. And I do say we. So when we have these incidents, frankly, we at PHMSA look at it too as well to see, we together as industry and regulators, how does this continue to happen? What can we do to help prevent it? We're looking at that as well. But one of the areas we focus on is the second column to from your right, or third column, is tech transfer and commercialized technology. So it's good. We fund a lot of different university projects and others, proof of concept. But one of the things we're trying to push for in our funding too is what can be commercialized. So we also track some of our tech transfer commercialized technologies that we help fund that get help to that next step. So through the years since our R&D performance has looked since 2002, we've funded 31 projects that have resulted in tech transfer commercialization technologies. Just get some examples of ILI-related projects we've done. Cathodic protection, current mapping. One of the reasons bringing this up as an example is sometimes we know where corrosion happens, and sometimes it's from issues with rectifiers or the actual CP you're putting on the line, but sometimes it can come from other sources. You have no idea where it's coming from. Stray currents from potentially another system that has cathodic protection, could be overhead wires, things like that. So some technology we look at to help map where some of those defects are happening. So when we see issues with corrosion, sometimes it's not only an issue from what an operator might be doing on their current line, it can be from some of these other sources. So this particular project helped look at it. It also helped look at diagnosing some of the problems, coatings, and others. So not just seeing, okay, there's an issue, but seeing where it's coming from and what are the issues behind it. Another ones we've done were, at least traditionally through the years, there are lines out there which we're trying to make all lines piggable ideally, but frankly there are some that are still unpiggable. So we funded some research into lines robotic systems to help inspect unpiggable transmission lines with a number of large sizes and other abilities. And other two through the years looked at improving, so continually look at how we look at sizes and defects and also characterize them and to help prioritize them. So we can see the defects, but how can we prioritize those to see if it's an actual leak? A lot of things you heard about here as well. So again, that's just the touch base of some of these examples. If anyone's not aware, you go to our R&D website. There's a link there below, and you could search in any topic area to see what we've done in some of those areas. Just a couple of areas. Excavation demos we've mentioned a lot today, so we funded some research into GPS-based excavation encroachment, looking at where it's happening, how it's happening, and also seeing help ultimately minimize some of those damages and ultimately improve pipeline or public safety. We also look at leak detection, so issues with methane emissions overall, trying to improve that both, in this case it's a ground-based system, but also looking at where those leaks are in the area. And we're also funding some research to help visualize some of the airborne based systems as well to help detect. This particular case, it's a fixed wing, but we've done a number of different research for a number of different areas. So that gives just a sense of where we are from a research perspective. But now let's talk a little bit about kind of gaps we see here. I think some of the biggest thing, you heard a little bit earlier today already about info sharing. So sometimes we don't know what we don't know. Sometimes we don't always get the information about what technology may have missed. I and a few others are part of the voluntary info sharing working group you may have heard of. One thing was interesting was a lot of vendors don't always get that information from operators and vice versa. So sometimes the vendors of these companies are interested in developing their companies, but they don't always get the information of maybe what have been miscalled in the field or other aspects. So improving that feedback loop from user to service provider could help a lot. And then that extends further to do others know about what some of the issues are. And I added one here, leaks or ruptures where newer technology is being used. Unfortunately, we continue to have issues with leaks and ruptures, including of some systems that are supposedly put in the latest technology and other issues. And you probably heard a little bit earlier today about the people aspect. Looking at technologies, it's not just the technology itself, but it's the overall system, which includes the people, process, procedures behind that. So what we often find are some kind of breakdown in our process, whether it's not proper training in a technology, not properly recognizing some information that your system is providing you that ultimately can create failures in the system itself. Sometimes it is not always picking the right tool for the right defect, or sometimes there's miscalls. Even if you think you have the right defect, either technology might miscall it, or there might be, sometimes it is a human error issue with interpretation of that data where it doesn't always, it's just not called properly. And then not always integrating the data available. So ILI is still a snapshot in time. When you're running that ILI tool, it's just showing you what is actually seeing at that given time. Now there is some integration of data before and after and ultimately seeing what has changed since, say, your last ILI run. But to the extent we can continue to integrate all the data available to us, a number of companies are doing it, but the ability to help integrate all that data to help look at some of those leading lagging indicators. So what were the leading indicators that help potentially develop this defect where it is now, and also lagging indicators to see what potentially can create in the future. So what can complicate advancement? Sometimes there is a regulatory lag. So you heard a little bit earlier today about prescription versus performance-based. There are some aspects of our code that sometimes can limit the ability to look at latest best technologies based on how the code is written and other aspects. We do have another technology notification process that I mentioned, but up to now it's only been limited to integrity management assessments in high consequence areas. And again, these are alternatives to ILI, pressure tests, or direct assessments, or some of the specific methods mentioned in our code, but they can do other technology notifications. I mentioned guided wave, there might be a couple others. If a special permit needed, in some cases, that can take a number of additional time to look at, sometimes up to 6 months to a year, if not more. And usually we try to look at any technology that comes in, we try to do due diligence to make sure, one, what has the operator done to review the technology, but also what do we think is needed for additional conditions and other aspects to help ensure pipeline and public safety before we're confident putting that technology in. And overall, it's just time to get comfortable with the technology. I think that's both not only from a regulatory perspective, but also from the operator perspective as well. So some improvements we are having, gas rule was mentioned a couple times today, but one of the big things, at least from other technology, is we're, one, reducing the time for notification. It used to be 180 days, and sometimes that can be more. If there's information in the applications that come to us that is missing, it might take more time, but we're cutting that down from 180 days to 90 days. And we're also expanding the scope of notification, so it's not just potentially using other technologies in integrity management assessment for high consequence areas, but also spanning to other non-HCA type areas. So any technology used for, and I wrote some examples here for spike hydro tests, looking at verification of pipeline materials, analysis of predicted failure. So now we're providing more of a vehicle to help look at some of these other technologies which we think can help improve overall, not just, again, integrity management with HEAs, but some of the non-HEAs you heard about. More means to help prove technology in realistic environments. So what's often proven in a lab doesn't always translate quickly to the field. And frankly, some operators, rightfully so, are nervous about putting a brand new unproven technology right on their pipeline. Potentially, can it overcall, or can it create some issues that then they have to act on as well? So any kind of vehicles to help prove technology in a more realistic environment, I think would be very helpful, and we are looking at a number of potential ideas behind that, but any kind of means to help that with all stakeholders involved can help. On our end, additional tracking of R&D funded tech. So I mentioned earlier about some of the tech transfer we look at of what gets to a commercially viable, but frankly we don't take it to the next step of saying, okay, this device is commercially viable, but is it actually being used, and is it effective? So we are discussing internally of how we can take the next step to help track of the extent to which these new technologies are used. Anything we could do to further reduce any kind of miscalls we see in ILI, and interpretations and field verifications to help improve seeing what we think we see, or if there's any miscalls, how do we help correct those? And again, I mentioned earlier, strengthening that feedback loop from the user to the service provider can help. And any kind of, we've already heard it, but any kind of ability to share lessons learned. You heard a lot about peer review groups, things like that, but typically those are often done within that circle of whoever's part of that peer review group. We don't always see that publicly. You probably heard a little bit about voluntary info sharing. There is still some unknown of what's going to happen with the future of that. But any kind of ability to help do this voluntary reporting of some kind, some of these near misses and other aspects, and then potentially share that to as many stakeholders as possible, understanding there are some nuances to that of antitrust and can't share too many details of specific issues and technologies, but still an ability to help share all that information and then continue to look at, we heard a lot about things like data rich, data heavy, but how do you help integrate that data to something that is meaningful to you, but also ideally do it into predictive modeling. Alan talked about earlier about we not just want to react to the last incident, we always want to help prevent the future one. So is there anything we could do with our data, help integrate it, to help do some predictive modeling to help prevent potentially where the next accident might be. So I know that was quick, but we also want to give a lot of time for questions at the end, and I did my best to help expand to a number of different areas. So with that, I'll hand off to the next person, and I believe we'll do questions at the end. Okay, thank you.
Grant, are you going next?
Yes, sir.
Let's see if we can find it.
Yeah, Coleman. There you go.
That should do it. Very good. This is Grant Coleman, is the Vice President of Technology for Enduro Pipeline Services.
Thank you. Thank you, everybody. Today I'm going to be talking to you about pipeline cleaning, caliper tools, and MFL tools in about 10 minutes. So that broad scope really did necessitate me pulling back, and it's pretty high level. So if you do have any specific questions, please bring them at the end. But we'll build through here. So starting, well, what are pipes? So here's some pictures of pipes. Originally we started off with trees hollowed out. We moved to stave pipe construction, onto steel, high strength steel and the modern techniques we know today. The reason I put this here is to highlight that the very infrastructure itself pushes what we can do with ILI. we are limited somewhat by what we have to deal with. The pipelines are living longer than ever anticipated. The 100 years pipeline is a reality. So these guys here weren't thinking of us today, but we have to still keep that pipeline safe. The other thing that really pushes ILI, of course, we've heard about regulatory, and that's a big one. And it's also our understanding and our evolution of our understanding of risk and how we handle it. So those are three drivers that push innovation. So what's a pig? Have to put this one in. If you're in South America, it's not a pig, it's a Diablo. You can imagine these things going underground, making the ground shake, and probably be pretty scary if you don't know what it is. So it's a Diablo. They started off as bales of hay, wrap some barbed wire, throw on some leather, and they evolved over time until we ended up with more modern things. But these were pigs that were put in primarily just to clean the line. There wasn't a lot more thought put into it than that. Focus on this guy from the 50s, late 50s I believe. It's a pig that was designed to clean municipal water lines. It looks fairly similar to a pig we would be familiar with today. It's articulated. It's hard to see, but it's like canvas and leather as opposed to urethane cups. Some pretty gnarly bolts and stuff going on there. So that was in the 50s. People are cleaning pipes, primarily just, get the gunk out. 70s, 80s, we started to move into more what we'd recognize today as a scraper type cleaner. But at this point, we're cleaning better, but we're not really doing the fine tuning that we do today. I mean, today we're looking at different cups, different configurations, trains, magnets, what we can do to make a specific cleaning program, which is quite important, surprisingly, as it's not maybe the most interesting topic, I guess, but the consequences of not cleaning really can't be understated. As we're pushing more and more into R&D, asking more and more from our ILI, the reality is any debris left in the pipeline is going to significantly impact the downstream data you have, your ability to use that data in the future. My colleagues here are going to be talking about some interesting work that's going on, but the cleaning of the pipeline is really foundational. If you build your building on sand, it's going to be pretty tough to go high. So you need to clean, and that's why it's important and it can't be overlooked. Okay, there's a lot of good resources online. Smart Pigs, Inga, SEPA both provide some great resources. Pretty generic. I'm going to talk about caliper pigs. It's usually direct physical contact with the pipe wall and their little fingers, and everyone knows, and it's designed to find mechanical or geometric things in the pipeline, dents, gouges, things like that. These tools have evolved as well. They all look pretty similar today, but originally they were single channel. You didn't know whether it was top of pipe, bottom of pipe. Now we have very high density, and that is a recognition of our ability to, or our necessity to know if something's on the top of the pipe is being more injurious than perhaps on the bottom. We've added inertial units to these guys and allow us to do full mapping of pipelines. Some examples of things you can find with caliper pigs. Pretty dramatic dent there and a stress relief. So construction, at the start I said, is important. It can come back to bite you. Okay, moving on from calipers. Next we have magnetic flux leakage tools. Everybody probably is familiar with it, but we're trying not to use the word MFL without explaining it. It's very simply using very strong magnets to see into the pipe wall. Initially we're just cleaning out the pipe, then we started to look at what was the pipe, geometry of the pipe. Now we're trying to see into the steel a little bit. And as we get to our other talks, we're going to be looking further and further into the steel. So we have a couple types. Axial being the flux leakage is a down pipe. It's with parallel to the pipe axis. Transverse, circumferential, is going around the pipe like a hoop. And then you have angled. I'm not sure the correct way to say that, but it's a mixture of both. So you can put a flux on an angle as well. And then the fourth style is this low remnant residual field. And that's looking at what's left in the steel after the magnets have gone away. So you're looking at the retentivity or the permeability of the steel that's left behind, and that can give you insight into material properties and things that are going on there. So how does MFL work? My lovely colleagues provided this from their website. Thank you very much. It's a picture showing flux in a nice clean pipe, the red lines being the flux, and pretty much all the flux staying in the pipe wall. You introduce a anomaly, a defect into the pipe, a corrosion, it causes flux to leak out. We put a sensor right there beneath it. We record 1, 2, 3 fields, store that on the tool, download it, apply pretty advanced algorithms, and we come up with a length, a width, a depth. In real life, it's not as simple. You end up with very complex areas. All these ones are different shapes, different sizes, leading to very complex looking responses. And every one of these has a different specification potentially based on what type of corrosion it is. Now, how we've evolved this technology, because it's been around a while, is by adding more sensors, tighter spacing, and then of course what we're trying to do is improve our specification, our accuracy at reproducing something like this. How do we tell? How do we assess our success? Assessing success, it's hard to say. So as I mentioned, tighter tolerances, that's something that's changed. We've gone from, generically plus minus 10, and that's shrinking. Our confidence intervals are going up. How are we doing that? We do a pig run, MFL, whatever it is. We go to the field, we dig it up, we measure it. There's error in NDE, there's error in pigs, but we plot them. If there's a 1-to-1 correlation, that's fantastic. You got a unity plot, 1-to-1. If you have debris, if you have something go wrong, you might be a little off. Your algorithms aren't always perfect. It's a nonlinear system and it's hard to get it nailed in every time. So you have plus and minuses. But one of the advances here is the line-specific, threat-specific, pinhole-specific algorithms. Those are the advances we're seeing. As we're adding more and more information into the systems, we're able to take advantage of it more and more. Now, unity plots are kind of boring, so I like that one better. If you're a Canadian, you might think it's the curling rink, shot rock and all that. So what I'm trying to show here is that in the past we had a target. Everyone wants to be in the bullseye, of course, but there's some scatter. And then over time, as the technology's evolved, a couple things have happened. The bullseye has actually gotten smaller. The whole dartboard's gotten smaller. But you notice the little dots are coming in tighter as well. And now as we've evolved our understanding, the sort of the thing finders have become pretty sophisticated. We have also new threats that we've recognized, new targets that we're aiming for. The first level, like any evolution, is can you just find the darn thing? Find it for me. Next, is it small, is it medium, is it large? Okay, next, how big is it? Refine it, refine. That's the evolution this industry goes through with every technology, from cleaning, from caliper, MFL, on through to the ultrasonic techniques. So thing finders that couldn't go very far, now we're doing 750-mile inspections. Are we making a difference? Yes. Obviously this isn't all ILI, but this plot's from Inga, I believe. It's part of the solution. As is everybody here, we all want to go for 0 incidents. What are we going to do in the future? Obviously we want to drive those little bullseyes smaller and the accuracy tighter. But it all comes down to leveraging all these different data sets we have. And that's a common theme that was brought up in our opening as well. How do we combine them to get more out of what we already have? And that's where, the buzzwords, big data, come into it. It's about making more with what we have and integrating the new with the old to get more. So, with that, I'll end, and I thank you for your time.
Thanks, Grant. I think next up is Matt Romney. Correct me if I'm going in the wrong order.
I think that's correct.
And Matt is the senior product manager for TD Williamson.
Thank you. So, Matt Romney, product manager for TD Williamson over our multiple data set and EMAC technologies. And I was invited to talk about interactive threats, specifically during this session. So the first thing we're going to define is interactive threats. What is that? And it's defined as where we've got 2 or more pipeline anomalies that are coincident with each other, and the combined effect of those two anomalies, it poses a larger risk to the pipe integrity than the individual anomalies would themselves. And so earlier this year, we had some colleagues that presented a paper, and they equated some of the pipeline integrity technologies to our 5 senses. So your sight, your smell, your taste. And this really resonated with me. So one of the things my family really likes to do is to go camping. And when we go camping, you load up the truck. Kids are excited. You drive up into the mountains. You get up into the pine trees. You can see the trees through the car window. Kids are still excited. But it isn't until we get out of the truck and you can hear the leaves under your feet. You can smell the fresh air. You can maybe hear a babbling brook, that it all sinks in. And my youngest will always stand and exclaim, "Smells like freedom," because he's sensing, he's feeling just that relaxation, the excitement about going camping. So Grant just talked about a number of technologies. And what we want to do is we want to leverage all of our senses or all those technologies together to experience or to inspect the pipe wall and the pipeline itself. And so very, very quickly, he talked through these technologies, so I'm not going to spend a lot of time. He talked about high field MFL, the axial magnetic flux leakage, and then non-axial magnetic flux leakage technologies. And these two tools complement each other very well. The axial arrangement does a really good job of finding those narrow features that are running circumferentially around the pipe, as well as metal loss features in general shape. In turn, the non-axial configuration of the magnetic flux leakage tools finds those very narrow features that run axial to the length of the pipe, something that the axial MFL configuration does a little bit worse job at. So the two technologies work parallel to each other and work together to fill in that full picture, to gather all the information that's needed. Grant also talked about a residual technology or a lower field magnetic flux leakage tool. That's going to be really sensitive to material properties that could be inherent from the pipe mill manufacturing process or from work hardening that's occurred on the pipe over time. He talked about the caliper or geometry tools, looking for those dents, looking for the geometric, the outer round, the geometry of the pipe itself that can provide context and information about the integrity of that section of the pipe. And he briefly talked about the mapping unit that maps the center line of the pipe. What we want to do is leverage all of this information, and the industry wants to leverage all this information together to provide the most value. And I apologize, this is a bit of an eye chart. It's actually to get you to come down later this evening. We've got this blown up, and you can actually read it later. But we'll focus in on one area. But what we really want to talk about is the value of multiple data sets, all of the different data sets that are available, and even including those that will be talked about later as we talk about some of the ultrasonic and EMAT technologies as well. As we leverage all of that and start using and overlaying that data, we get the best value. So we're going to focus in on the upper right-hand corner there and talk about interactive threats. And one of the classic interactive threats is the excavation damage, or something we'll often call mechanical damage. Classic example is the excavator that struck the pipe. And 20 years ago, that would have been recorded probably as a dent. Depending on the phenomenon that occurred, the pipe may have rebounded somewhat, and that might actually be a fairly small dent. And so as your lower resolution ILI tool were to collect that data, It may be recorded as a small dent and nothing more. Today we have different technologies. We have different opportunities to collect the data. Now that same feature will be recorded as a dent, but we've seen improvements in the sensor densities, in the sensors themselves. We're going to gather a little bit more information about the profile of that dent today than we would before. In addition to that, we've got these high-field MFL technologies, magnetic flux leakage technologies. We can start to see if there's some coincident metal loss, something that looks like a gouge. Overlaying those two data sets together, now I've got a little bit more information about that. I now can classify this as a dent with some metal loss, with a gouge. That elevates the risk. That elevates the interest in that feature. Leveraging that low-field technology, maybe that dent was larger at one point, has rebounded, and so around the edges of that dent, we're going to see some work hardening, or maybe it cycled some. Now I can detect that with that low-field technology, overlay that with the other technologies, and now I can really start to draw the picture of what this dent really is. Now something that may have been called a fairly small dent 20 years ago now gets classified as a small dent with a gouge associated with some permeability changes. Now that drives a wholly different conversation with operators on specifically what they're looking at. And these changes over the years are really the result of three things. So it's improvements to the technologies that were existing, magnetic flux leakage. It's development of different technologies or different applications of technologies, the non-axial version, the low field. And then it's development of processes leveraging the data. So classifiers looking at how these defects are classified and how information is communicated to the ultimate user of the data. And it's through these developments that we continue to see improvement. Are we done? Of course not. Of course we've got to continue, and we're going to continue to see these sort of developments in the industry as we continue to drive to safety. Appreciate your time, and look forward to questions later on.
We're going to swap computers because we're having trouble getting, maybe we just put it right on top.
Just like
There
that.
it is. Look at that, like we knew what we were doing. This is Jeff Sutherland, the products portfolio leader, process and pipeline services for Baker Hughes.
Great, thank you. My role for the panel today is actually talk about ultrasonics technology. This is the most analogous and what everybody might be familiar with from the medical industry. In the 1980s, it was first applied to the pipeline world for wall measurement, and as we get into it, I'll explain how it works and the different evolutions since. The first thing I'd like to touch on, though, is given the 20-year perspective, kind of went back and what was in our portfolio circa 1999. And the dates here are kind of the launch dates of those tool and technologies at the time. Crack detection, being ultrasonics there on the bottom right, was a fairly new thing. It was first run in 1994, and I'll explain that a little bit in a minute. When we move up to what it is today, a few more tools, new technologies added to the portfolio. A lot of things happened since 1999, as you'll notice, like all the dates are through the 2000s and into the 2010s. Across magnetics, across caliper, across UT, across EMAT. There's been a lot of kilometers collected. I'm sorry, I'm Canadian. Miles collected. Sorry, I'm Canadian, because that just is self-explanatory. With that, my role today is to talk about the ultrasonic part of the inspection families. So with that, I'll be talking about a couple different ones. One is known as wall measurement, WM. Not a lot of thought goes into these. CD, crack detection. And for context, I thought it would be best to actually provide some objectives, because we talk about pipeline threats, or we talk about cracks or corrosion. And the analogy I use is, again, a medical one of, in the 1950s or 50 years ago even, there was one word for cancer. And now there are about 207 different subtypes. And the nature of what we are looking for follows a similar thought process. There's a lexicon or morphology about how to describe these things better, and with that becomes better learning and more specific applications, and again, better treatment effectively for the equivalent. Just the analogy here is there's something called a hook flaw that happens in ERW pipe. It's a very different phenomenon than what's known as SEC, or stress corrosion cracking. The ways and means that you actually look for it, the ways and means you interpret data from it are quite different. And as such, we can start focusing more and more specific technology or specific analysis techniques to look at it. So, pipeline inspection, ultrasonic pipeline inspection. First I want to talk about is wall measurement. This is a very classic, if you've ever seen an actual ultrasonic sensor, it's about that big, size of a battery. It shoots out ultrasound, comes back, it's just like a medical one. This is actually going in through the pipe wall, as shown in the top right. Sends a signal in, a signal comes back, we interpret that signal as a change in the actual thickness of the wall. It was first released in 1988. It's varying levels of resolution. It's like if you think about what kind of video recorder it had in 1988 compared to today, it's very different items. Today we're actually finding pinhole defects. Pinholes were mentioned earlier. These are like basically the tip of your pen type of diameter type of features. Crack detection is the application of these ultrasound sensors just at a different angle. We shoot them at a different angle so they actually bounce in and out of the actual pipe wall, and as they do that they actually reflect off of crack and discontinuities in the pipe wall. Its initial run was 1994. Through the 1990s, it was an evolving technology. You might only be able to do 60 miles because it took a lot of power, still takes a lot of power to run these. It was detection only, so you had a blip or you didn't have a blip, as mentioned earlier. It was a thing finder for cracks. And you got your list of what cracks might be in your pipeline basically a year later. Today, it's basically going at full line speeds. We've done 600 and something miles in a single pass. It's finding things less than an inch long, and you get your report in a couple of months. And again, we always compare these kind of levels of data, but it's like we had to invent storage systems at the time because you didn't have a cloud or you didn't have the level of like what YouTube has. So both devices as well as servers were custom made. The more advanced levels of ultrasonic pipeline inspection was phased array, and this is, again, medical analogy. You can actually control where the beam goes from the sensor itself, similar to when you have an ultrasound for yourself or you're looking at a baby, same technique. You can find that with an imaging. You can shoot it as a WM method, meaning in and out, and you can control or basically analyze and interpret for wall loss in the pipe, or you can actually interpret it and shoot it as a crack detection mode. Either way, you can actually do them at the same time, and you can actually shoot it at different resolutions. So there's a lot of power and flexibility in such a system on one tool. Last but not least is the next generation of WM and CD. The primary analogy in this is it's basically finding things like a dime. So something that is the length of a dime, a crack, the length of a dime, and the thickness of a dime. And that's the minimum defect spec that that system has. So it's very hot, fine resolution. I typically use like the analogy of the lines on your hand are not really that deep and they're not really that long, but that's the thing it's finding between here and Houston in one pass, just to kind of give a level of the technology capabilities. Similarly, WM, we mentioned pinholes before, very fine tip of the pin type of defects. And I believe that was it for me.
swap back to the other computer. Goes as smooth as that one did. We'll. Yep. Yep. Oh, that got disconnected.
That's it.
That's it right there. It's Christopher DeLeon. He's the head of Integrity Solutions for the ROSEN Group.
Good afternoon. So I hope y'all like pictures of smart pigs, because there's going to be a whole lot of them in this presentation. So today my chat is focused on an ILI technology focused on finding crack-like defects, or non-volumetric, also known as planar. And the theme was definitely around building and maintaining confidence. That kind of is the segue from the conversations that we've had earlier today into today. And wanted to highlight a little bit that topic of confidence, right? So in these ILI systems, we heard Alan this morning or mid-morning say that it's good at finding things, but we need to get better at it. So the idea with this presentation is kind of walk through some of those ideas. So I do want to touch on 3 topics today. Number 1 is an ILI system and the history of this specific ILI system. Number 2, more importantly, is continuous improvement and that need for all ILI systems independent of the technology type. And then 3, being able to couple any ILI system with sound integrity engineering. So hopefully I can deliver that message. So this is what an EMAT ILI tool looks like. EMAT is an acronym for Electromagnetic Acoustic Transducer. That is the measurement principle by which this tool operates. I think what's important about this is it was designed for finding generally axially oriented cracks. But what we later found with the measurement principle of EMAT is that it can also detect and identify locations of disbonded coating. And based on experience, we were then able to correlate and begin to identify different coating types. So this is an often typical type process of when an inline inspection system is developed. So you often have, number 1, the tool itself and how it behaves. Number 2, some kind of sensoric technology that is measured, that is based on a measurement principle. And then number 3, all the algorithms and processes that come downstream of that. And sometimes through those algorithms and processes, you can get extra or secondary value from the original intent. And that's always great. So thinking about continuous improvement when you have an ILI system, pardon the image here, I'll do my best to explain it. So what we have here in the center is ideally what would traditionally be reported in a final report. That's what the FP stands for. And depending on the system and the measurement principle being applied to a specific threat, whether it be a geometry feature, a crack feature, or a metal loss / corrosion feature, and how mature or precise that system is, what you want to try to find is you want to have an absolute identification of true negatives. True negatives meaning when I think something is not there, it's actually not there. And you really want to then be able to hone in on the true positives, meaning if I think something is there, it truly is there. And often in these ILI systems, there can often be overlaps depending on what you're trying to find and what ILI system you're deploying. And ideally through continuous improvement, what we want to try to do is avoid the false negatives where it really was something, but you inaccurately called it as it wasn't. And then you want to minimize how many times you don't have something, but you say that it is something. And so through a lot of effort, you can try to think of that as it's, for example, you want to not call a crack something that is corrosion and say, oh, it's just corrosion when in reality it's crack. Or on the other side, you don't want to say that something like a manufacturing artifact like the geometry of a trim of a seam or a pipe property is actually something that you go and waste resources on to go and investigate in situ. And so as you gain experience and you continuously improve your technology, what you hope to do is, again, be able to separate those two so that you truly understand where your true negatives are and where your true positives are. Does that make sense? So ultimately, that's what we as technology providers really want to do. and that's a process, and it's collaborative. That's what we alluded to earlier, is it's the more collaborative that we can get with industry, the better technology we'll be able to advance and satisfy this ultimate need of trying to purely identify true positives and separate out the true negatives. So if I focus a little bit on EMAC history, coincidentally, at ROSEN, we began development of our EMAC technology 20 years ago, so it was a nice theme. Kind of what I think is important here, and what I'm going to try to portray in this chronogram is, Alan said, integrity management is built on the premise of continuous improvement, and that's kind of what we've seen with our EMAT technology and most ILI technologies, if we were to look at them. So at ROSEN, we typically approach building an ILI system for a specific threat to a pipeline by first going to a measurement principle. We want to identify what is the measurement principle that we want to then develop into an ILI system that can be deployed into a pipeline. After we understand what the measurement principle is going to be, we were focusing specifically on, can we identify cracks using an ILI system without an elastic median, i.e. a couplant like an ultrasonic. This would be very applicable to the gas market. And so we did. So EMAT already existed as a technology. Our goal was then to put it onto an inline inspection device that could be deployed through pipelines. In 2005, we had our first commercially available tool in a 16-inch, and our first inspection in 2006. So a little bit of history there. That was our first tool. From 2006 to about 2010, it was really about just making more of these tools available to some of those operators who are a little bit more on the front end, who, while this wasn't industry standard or required by regulation, these were operators who were stepping forward saying, we recognize we have this challenge in our pipeline, this is what we need, so pull and push. So we developed tools according to those sizes. And as we gained experience, what we identified was that in around 2010, if we could simply improve the behavior of how a tool propagated through a pipeline or navigated through a pipeline, our ability to separate true negatives and true positives went up. And so a big example of how we did that was through identifying suspension systems and improved sensor ride from the ID of the pipe. And so what then we found was, it's post-2010, you started seeing that a lot of our tools were really based around reducing friction and reducing vibrations. And one example of how we can do that is by using wheel-based suspensions. And so if you think of something that's dragging versus something that's on wheels, you reduce friction, you reduce bounce, and so your sensor has a better ability to acquire the data that you're looking for. By doing so, you can then potentially reduce the type size defect you're looking for, and you'll have a more accurate description of that type feature. So it was very much around run behavior. Looking forward now, right about 20 years later, we're to the point to where we've kind of got our measurement principle and the deployment of ILI technology into all types of shapes and sizes, right? Whether they're single diameter small, down to 10, 12 inch, or they're very large, like 56 inch, or they're multi-diameter, where you need to traverse a pipeline that's a 30-inch pipeline with 24-inch valves, and the tool needs to be able to collapse. So all those in-betweens, we're kind of there as an industry. So what we're now focusing on is next generation sensor configuration, right? So what I mentioned earlier is, one, you have a tool. API 1163 defines an inline system as the tool itself, so the behavior, the mechanic part of it, the sensoric technology, the evaluation processes, the algorithm, and the software that are associated with providing you guys with the final report. So with that, now you'll often see that ILI technologies then start looking at, how do I improve the ability to acquire data, maybe from a sensoric perspective or from a configuration of sensors. So with EMAT specifically, we're now looking at things like finding redundancies up to, for example, 200%, shooting our acoustics both clockwise and counterclockwise to get different looks at the type features, which gives you more data that you can render. Increasing sensitivities. Colleague here, Jeff, did a great job of giving practical examples of what we say when we say things like 1 millimeter by 20 millimeters, for example. Very, very, very small type things that we're looking for at pretty rapid velocities and across long distances. And then obviously, as industry is pulling and commanding, optimizing these ILI system towards specific threats. So as we heard even Alan say this morning, we're finding things in seams, but we need to do a better job at it. So definitely optimizing systems there. So continuous improvement is key. So up to now, many of the ILI systems have really leveraged this concept of tool behavior continuous improvement and sensoric continuous improvement. Some of the things that we foresee coming in the near future are things around what we often like to call now modern analytics. And so that's one of the big initiatives that we have. So we take things like machine learning through ideas of like spatial recognition of one behavior of signal types and the actual physical dimensions of signal types. And then we can then, based on their spatial correlations, begin to break them up into different types of features. So when you deploy an ILI tool, you can say, we are most likely that these type of features have this type of congregation, and therefore those are often hook cracks or laminations or lack of fusions. And so you're able to look at all of the different expressions of features that you'll have in your pipeline. For example, one case study that we did on this was we had a sample set of 216 features, and we did not apply our normal human-based analytics. We sent it through machine learning, and we were able to come up with 186 features properly identified and sized within a Unity plot under standard specifications. So what that does for you is, one, it can reduce human error, and two, it also creates a more reliable and consistent system by which we can deliver information. But then ultimately, three, is its response, right? So as we're deploying these technologies, you're able to gain information a lot faster. So those are a couple of examples of how the CRAC or EMAT technology has been able to continuously improve since its inception. And often what we find as technology providers is that one, North America is definitely driving a lot of this innovation sheerly by the demand of service. And so what we do here is really important as an industry. But then second, a lot of these technologies are vetted globally, and they're often seeing all kinds of different problems. And so what you see in one part of the world enables you to potentially help another part of the world solve those similar type issues. What we've also found, if we look at integrity management from 2004, traditionally CRAC has not been on everybody's radar. I heard a chat by, I think her name was Nancy from now Centerpoint from Vectron, that safety management cultures really changes how you make decisions. And so now they're not waiting on regulation to take action, but rather it's a mentality. And I think we're beginning to see that if you also look at the mileage and the use of these more non-traditional type ILI systems. So it's definitely exponential. Last topic for today is Alan definitely said that we need to be able to find smaller defects, but I think what's important as a takeaway is it's when you deploy an ILI system, it's important to understand that that should be part of sound integrity engineering. And so when you're looking at a specific flaw in a pipeline, it's equally important to understand what's the load that feature is being put under. But then equally important, if not even more important, is understanding what are the material properties and how is that material going to behave under that load and with that stress concentrator or that specific defect in the pipeline. And too often, we as an industry are relying too much on the ability of an ILI tool to simply find something smaller to have increased conservatism on the back end than truly understanding the environment in which these features are having to behave and survive. And so if you can do that, then often what you're able to do is then make good decisions. And if we can do that, then we'll be able to prioritize resources and we'll be able to find more value in these ILI systems. So with that, I'll conclude and say that our mission often is to empower decision makers with technology, but our ability to do that really requires a participation from industry, not just from the service provider side. In industry, I mean all stakeholders, whether it be regulation, best practice, consensus, operators, public. It's really the culture and the environment that we operate in. And if we do that, then we'll all get the most value out of, one, technology providers, and then also you guys as technology deployers. So with that, thank you for your time, and I hope you found it useful.
Thank you. And last but not least is Tim Clarke, who's a senior integrity consultant for Boardwalk Pipelines, and he's an actual operator that has to try to figure out all this stuff and put it all together. So he's going to kind of wrap this all up for us.
Yeah, it'll be fast, so we can get to the liquor. Wanted to come talk to you. It's kind of ironic that I was volunteered to come up and talk to y'all about ILI technology. About 20 years ago, I was sitting in a conference room with regulators reviewing the Olympic pipeline log that Tuboscope ran. And I don't know if any in this room remembers the paper logs. You know, that's what we were using back then. It's come a long way. We just hit the clicker here. So we're going to talk about a little bit about that, and one other thing that, like I said, I was on the service end of it for 10 years, and when I made the jump over to the operator side, I go into my boss's office, and I tell him I want to do this and this and this, and he looks at me funny. He says, I don't care what you do. This is your deal. You make the decisions. And right then and there, I made a commitment to myself that I'm going to look at every log. I'm going to look at every anomaly that goes out the door. So nobody else is going to jail. Nobody's going to get hurt. And that was my goal. So from that point, we go with Gulf South and Boardwalk.
Up and down.
Oh, up and down, sorry. Okay, this is a Boardwalk Pipeline system. You can forget about the MLP there. That's his old map. But the lines itself is, we've got liquids as well as natural gas systems and storage. One of the reasons I put this slide on here is in the development of the last 20 years is he touched on it, 1163, and then also the most important one was this one with his personnel qualifications. At that time, I liked that one because I was involved in it. Basically, at that time period, there was nothing out there to guide operators or to guide service providers. And I think it was a real good deal to incorporate that. And every vendor that worked for us, after those were brought out and published, they were part of our contract that they had to go by. Okay, now the improvements, these guys have talked about it, and you're going to hear a lot of the same thing. Tool developments. What we look for is what our system can handle. The tool developments like flow control, drag reduction, that type of stuff. That's what we look for in the natural gas system, because the bottom line is if you're getting speed excursions in a natural gas line, you're getting bad data, and that's what you're trying to avoid. The next one is data storage, going from the 90s where megabytes to thousands of gigabytes now, on capabilities of putting more technology on one tool, which is a real plus for an operator. Battery life improvements, from running a tool, high resolution tool that can only run 16 hours to being able to run 632 miles. That's a big difference. And one of the most important things is the improvement in sensors, both magnetic and ultrasonic. As a natural gas pipeline, we don't run a whole lot of ultrasonic, but we do run the magnetic flux fields. And then the next item there is more sensors improving analysis and ILI data, which is a big part of it. Improvement in magnets, where they're going to the rare earth magnets, the sled-based tools for better collapse is a big plus for an operator. The next one, caliper, where the sensors were behind the cup, compared to the deformation tools that the sensors were writing on the pipe wall. Makes a tremendous amount of difference. You're going from a 2% dent basically to 0.5 of 1%. So the accuracy is a lot better with that. And then finally, the combination tools, which most of these guys have. And by the way, I have run all these guys before, and I'm not going to badmouth, okay? But the combination tools, and once they came about, was a big plus for us as an operator. This is one of my favorites, inertial navigation system. I think what this does is gives you GPS coordinates on every feature on the pipeline, and you can do so much with those coordinates if they're accurate. And that's the object of running it. So what it helps is it helps on risk factors in HCAs, but most important, it helps on risk factors outside HCAs. If I've got a pipeline running next to a guy's bedroom, and I've got an anomaly there, I can plot that in with the coordinates and say, hey, I may need to make a decision. I need to go get it. Very important. Data integration, another big key factor that you can do with the GPS coordinates. Pipeline strain, we've done that on a lot of the lines that are in rock, in river crossings, things like that. And again, viewing the anomaly or where the location of the anomaly is. And then last but not least is the ground movement areas, which is a big interest to people these days. The GIS and data integration system, this is our pipeline system again. As you could tell, all the tool runs are on there, all the pipe repairs, rerouting, everything, all the information on our system is within this map length. And everyone in operations and in the company has access to that, which is very important. Oops. I put this slide on there for data integration. All the other, this blue line is our pipeline, our natural gas line. All the other ones are other operators within that. And even commercial with other operators on there, water lines, everything's on there, that you can go back in there. You got a satellite imagery of it. You can go back in there and see and compare it to the log to see if there's possible third-party damage there. Very, very good tool. And I guess this is the most important one for you picking vendors. As I think Chris brought up and several people brought up, the accurate pipe information to the ally vendor. That's very important as an operator. We get the right information to the vendor. And again, the accurate reporting of the vendor, the preliminary report, the final reports, of course, are the key. 4 years ago, we had an average of sending back 60% of the final reports that came in for inaccuracies. I wasn't going to talk about y'all, was I? But no, that's what it come down to is, you go from that 60%, and now we probably have not even 5. What these guys have realized that we do look at the data. We make sure it's accurate. And this one here, I've been doing since I come on board as an ILI manager. Carl noted that I was a consultant now, and I'm beginning to really like that term, consultant. But ever since I've been at Gulf South and Boardwalk, I've always reviewed all the data. And that's where we find a lot of anomalies that a lot of other companies don't find because they don't look at the raw data. Girth weld anomalies, seam anomalies. That was a must on anybody that worked with me. And then this, again with 1163, this is a real important part of it. You got to give the dig results back to the vendor. If you don't, you're shooting yourself in the foot as an operator. This is the accuracy chart of the ILI calls versus what was repaired. Again, you go back to 2011, based off of 2,200 digs, that what we repair versus here versus what we do now. Now, this is on the conservative side. We have changed some of our criteria of what we repair because we're already in there. But that's a good scale of, you know, that it is improving. And last but not least, always remember, whoops, no matter how good your technology is, always pig and dig. This is the ally group, and that's the pipeline services group there. How's it, Carl?
All right. Thank you. We've got time for a few questions. I'm going to jump off of the first one because something that Tim just said kind of surprised me because I've been told for years that there's only a handful of people in the world that can read ILI data. And they're mainly vendors. I mean, you're saying you're looking at it. Is that becoming more normal for companies to have people that can deal with the ILI data internally?
I agree with that. I think you're seeing more and more people getting analysts on board. I've got basically in Boardwalk, there's 4 senior analysts that can read ILI data, and including myself. I've been doing it for 20 years.
Questions? I'm warning you right now. I've told the bartender at the Carousel Bar he's going to have a post-test on all this stuff that he's handing out at 10 o'clock at night. So, no questions. Everybody's thinking that it's time to go down and actually spill some beer on some pigs. Here we go.
And this is just coming from somebody that knows nothing about it. Just so I can understand better, the ILI tools, the non-physical tools, how far off the walls of the pipe are the sensors? Are they really close? Is it, you're running like half an inch, or is it 2 inches? Is it, just kind of describe that for me, how the pig fits in the pipe and all that.
Anybody?
I'll start.
You go there.
I'll ease us into it. So I think what we tried to do today was do a little bit of an exhibition of there's different technologies for different threats. And yeah, you can get value in incorporating them to make better decisions, but each measurement principle has different tolerances. And so within what I mentioned earlier in API 1163 is it's an ILI system, not just the tool is what you want to look at. And in that system, you need to appreciate how the sensor works and its tolerances, your algorithms and its tolerances, and then your error or risk associated with just overall processes. And so it's not an explicit way to answer your question, but I think that's part of that relationship, collaborating with each of your ILI vendors, right? Which was the second loop that I had, right? So one is empowered by technology, but 2 is that participation and asking exactly those type questions. Every technology will be a little bit different, but in most cases you will find that for us, we maybe will pick between 1 or 2 millimeter standoff or differences from the wall thickness. but in reality, in most cases, you could in most cases say that they're virtually touching, even though they might not. So, for example, ultrasonics require some kind of couplant. Like when you take your wife she's pregnant, she takes to the hospital, they got to put elastic media on you, or that couplant. It's kind of cold, or they have warmers. You're physically not touching the pipe with the ultrasonics, but I mean it's so close that it's virtually touching, right? And standoff, actually, what you bring up can be a significant issue, which is what I try to bring up, right? So we as technology providers, we really try to optimize our tool design so that we get a better internal ride, right? So a good example I like to give is if you got really good shocks when you go over a speed bump, your wheel kind of like follows the profile of the bump, but if you got a real stiff sports car, it just kind of like bounces over it. So that'll affect your ability to acquire data. So.
Anybody else?
First off, thank you. That was a really quick summary and wonderful detail at the same time. I have a question. In our neck of the woods, I live in Lafayette, California, and we have a topography that it's kind of up and down and very short segments of pipeline. The issue there is the pressure or the diameter isn't accommodate ILI. So what are the technologies that are available to really get in to know the detail of older pipeline? So I don't know if that's a question for you or.
I'll start, and I know one of these guys wanted to say something. There's been two terminologies that have kind of floated around our industry since at least I've been around for the last 11 years, and one is difficult to inspect, and one is unpickable. And what I personally struggle with that now, being with the technology provider, is that I think that difficult to inspect is more appropriate. Because as lines get more challenging to inspect, I think that should be owned by a relationship between the operator and technology providers. Because as I tried to allude to earlier, we're developing tools based on what the market needs, not making the market conform to what our tools are, if that makes sense. So whether you have big significant drops, or you have very deep pipelines or very high pressure pipelines, or different size diameters, different size wall thicknesses, that's where I think we try to take pride in ourselves in really working with operators to try to find solutions. The challenge there's always time and resources, right? Unfortunately, those are just part of economics. But I would say that there's a lot of technologies and there's a lot of service providers who can generally help try to start squeezing that gap a little bit, as long as we have the right resources and the right amount of time.
So follow up to that real quick before you go away. So when you say, so we often hear operators say, well, my lines are unpickable. Are you saying that's a function of how much they're willing to spend to get a pig to do it?
You won't take that question. So,
It's participation.
oh, okay, I appreciate that.
The coalition of the reluctant.
So the answer is, as Chris had kind of alluded to, is communication. The ILI vendor knows their tool. Each of the tools specifically, we have a pretty good sense of how that's going to navigate a line. What we don't have is the details, or some of the nuances of that line. And so when we have good communication with an operator, we can find solutions, even to these difficult to inspect lines. We can, talk together and find ways to identify ways to improve the ride or the pipeline, pressures, flows, the different details to drive towards the most likely positive outcome. And that's really how we overcome some of these difficult to inspect lines.
On our Gulf South system, we've got small diameter, low pressure, low flow pipelines, and we've had to take them out of service. And we use two different technologies based using nitrogen to run the tool on it to be able to get the volumes to run it, to negotiate the line, or we use a wireline truck and run the wireline through the pipeline with air. Of course, both of these are taken out of service. You run it through air and you pull the tool back, And so to say that a line's unpickable, I don't know if that's true. You know, you might bring the cost of how many miter bends you might have in the line that you can't pick through. You know, that plays a fact in how you make your decision, and because that can get costly.
I just want to add one part. And
Chris,
to that
you
is,
gotta give me a moment
yeah,
here, too.
and I will. I will.
I finally got them going.
It's not an ILI plug actually. It's the other end. What's also important though in these challenging lines is what happens downstream of the inspection though, and I really want to just shine a little bit of light on that. So yes, there are limitations to inline inspection systems, but it's also often what you choose to do with the data once you have it, whether it has limitations or not. And I also think that's equally as important as to the system you deploy and the results of that system that you deployed.
I got my own, I found out. Still on. I just wanted to add one point to your comment about the unpickable, difficult to inspect, is there are other technologies other than ILI. And I mean, we're all ILI vendors, and I'm going to fall on my sword and suggest something else, but you know, little smart balls that are being developed that roll along with magnetometry, they count footage, you know, and all that good stuff. Completely different, but it's an innovation in our industry that maybe provides other solutions. And so those little companies, little startups are out there that are trying to answer exactly those things. So it's yes, of course, we're picking ILI companies, but the reality is there are other ways to fill those little gaps. And I think those are what we really need to explore as well as an industry.
Yeah, and I'll just add, that's where you have to get into some of those other assessment methods I talked about. So there's pressure tests, which some argue whether that's really effective. But direct assessment is some of the, so that's where what's known as external corrosion direct assessment or internal, but that's where an individual has to physically walk the line and look along that and look at some anomalies. You're probably not going to get the resolution they're talking about, so then you have to decide, are you going to dig or not? Guided wave is probably another one that you might want to consider using. Some limitations of guided wave, you can only go, limited shot each time, so you're probably going to run it a few times along that line, particularly when you're having it hard to reach areas. So, so those are just some other opportunities. Guided wave, yeah, this is where some operators might use for particularly hard areas where they can't, whatever reason, can't run the full pig, or other areas where they just can't quite see or do direct assessment. So that's where it's used under highways, things like that, where you just can't get on top of the line. So. But again, it's only short segments, so you're going to have to do it several times along. So, yeah.
Maybe a reference, actually. Sergio Limon, I think just in the interest of time, I wanted just to share a reference in 192 for gas and 195 for liquids. In fact, not every single corrosion or metal loss or cracks that is reported by the tools presented are actually reported. And the regulations at the federal level outlined what those conditions will be for which then should be repaired for gas lines, which one for liquids, which corrosion for gas, and so on and so forth. So for the general audience, or those who are not familiar, they can go into the 192 IMP rule and find out what those conditions are. And 195 similarly. I think it will be a great reference.
If anybody wants that, I'll send it to you. We're over time, but it is the last session of the day, and we have the room till midnight.
But can you bring the beer here?
Yeah, and I'm going to encourage people, maybe we can call it, I think the providers are going to be ready with their tools at 5, if they're not already.
I believe they are already.
So you can go down and actually see what these look like, hands-on, and I think the drinks and the bacon-wrapped shrimp and all that good stuff is supposed to be down there by 5:30. So thanks for being here, and thanks for the great short presentation, because I think we could have spent 2 days on this easy.